familiar waveform of a sinusoidal source. Yeah. So here's a current source. You can see the current is indicated there. That's the scale. Time on the x-axis. Yeah. Current magnitude on the y-axis. And then you can see the peak current. We often refer as amplitude. Yeah. And then what is this one? Time period. Yep. And it's one cycle. So often a cycle is the time or duration it takes for any waveform to go through all possible values that it should go through before beginning to repeat itself. So past this first cycle, the sinusoidal waveform will repeat itself again. So that'll be a second cycle and so on. And for a power signal at 50 Hertz, yeah, time period is given as 1 hour frequency, which is 0.02 seconds or 20 milliseconds. So this whole duration from there to there is 20 milliseconds. And you can see that half of it will be 10 milliseconds, where you can say that the sinusoidal waveform goes through positive values in the first half, which is basically the first 10 milliseconds, and then through the negative values in the next 10 milliseconds. And that behavior of positive or negative might be different if you're looking at a cosine waveform or a tan waveform or something. And then obviously 5 milliseconds is the first quadrant. And as you can see, within 5 milliseconds, the voltage or current, whatever you're looking at, reaches its maximum. Now this has relevance to why certain circuit breakers or fuses should act within a certain time. So if you have a circuit and your circuit knows within the first 5 milliseconds what is the maximum value of current that's going to go through it, or the voltage that it's going to be subjected to, after that it knows what the maximum value is. If the maximum value is increasing, for example, let me choose a different ink color. Let's say there is a fault, and that's how the voltage or current is increasing. Then your circuit protective device, whatever it is, be it a fuse or a circuit breaker, should be able to pick up that information after the first 5 milliseconds. So usually circuit breakers operate in the first 2 to 3 cycles. So if each cycle is about 20 milliseconds, 2 to 3 cycles would be 40 to 60 milliseconds. And if you compare that to a time scale of a second, you know how short that window is, which means how quickly these circuit protected devices should act as well. But they are physical constraints, or sometimes constraints from the physical properties used to manufacture those devices. It could be a material property or so on. But if you look at the waveform itself, the information is available for the device to act in the first 5 milliseconds or first few milliseconds. And often, those first few milliseconds are the ones that can destroy your equipment as well if the voltage is too high or if the current is too high. So the quicker your protective device can act, the safer the whole system will be. Okay, so that's about sinusoidal sources and the various parameters associated with a typical sine wave. Hope that is clear. And go on to the next one. Now, the waveform here is also a sinusoidal waveform, except that it is shifted to the left. Yeah, So there are two ways of looking at that shift. It's relative. So the two things here to look at are, one is where the axis is drawn. So if you look at the previous slide, you have a x and y axis, and then you have a waveform. So if you think that the x and y axis is one plane, and the waveform is something you put on top of it, now you can either move the x and y axis to the left without moving the waveform, or to the right, or you can keep the axis where it is and just move the waveform to left or right. So if I move the waveform to the left, what happens here is you can start the waveform somewhere here. Yeah. So it begins before time t equals to 0 and finishes before it's due to finish its cycle. So that's called moving left. At the same time, you can also move it to the right. So you can have a waveform that starts after a certain time delay. So it's all about where the waveform is starting. So if sine is not starting at time t equals to 0, it can start after a delay, or it can start ahead of the starting point. And that is what is related to the words lag and lead, and then that's related or associated with the phase angle. So often you call a phase angle lag or a phase angle lead, and therefore lagging power factor and the leading power factor, which are the terms you'll become familiar with later on. So that's how you can do the shifting. So here we have a waveform and an xy plane, and you can think that the waveform is shifted to the left. Yeah. If it is a sine waveform, it should start at this point, so the shift is this much. Contrarily, if it is a cosine waveform starts like this, yeah, at t equals to 0, cosine 0 would be is 1, yeah. So at t equals to 0, the cosine waveform has a maximum value. At t equals to 90 degrees, cosine 90 will be 0. So you can see this is what happens. And at t equals to at 180 degrees, which is, let's say this is nothing but pi by 2. This is pi. Cosine 180 is minus 1. Yeah. And then cosine 270 is again 0. Cosine 360 is again plus 1. Yeah. So that is your 270. And somewhere there would be your 360, where it is again plus 1. Okay. So what we have seen here is a sine wave, and this is a cosine wave. So therefore, a sine and a cosine wave are sort of interchangeable. So the same sine wave, I could have moved left by 90 degrees to start somewhere here and have the maximum point at t equals to 0. And then for anybody looking after the x-axis mark, that looks like a cosine wave. So if I show it, let me show it on this slide. So that's your sine wave. And if I say move the sine wave a bit to the left and start such that the sine wave is starting here, yeah. So what I did is I moved the sine wave to the left. But then when somebody looks at it and doesn't see this portion, yeah, let's say this portion is blocked for them, then all they see is a waveform starting at a maximum, going through here, and if they continue to see, they'll see this, which is exactly what we saw for the cosine wave. So a sine wave, when you move it by a certain angle, can be written as a cosine wave. So when we talk about the power waveform, often when you talked about sinusoidal sources in your first year's course, you talked about sinusoidal sources, and any source is represented as something like voltage maximum, sine omega t. Yep. So the same thing can also be represented as cosine omega t with a change in a certain angle. So and that certain angle will be this angle. So a sine can be represented as a cosine can be represented as a sine, as long as the phase shift or the movement is taken care of. So for now, all you need to remember is that difference of theta. Yeah. So when somebody is looking at this waveform, you can look at it as a cosine wave that starts at this point, which has been moved from the origin to the left by a certain angle theta. Yeah. And that can be written as cosine omega t plus or minus theta. I'll tell you in a minute whether it's going to be plus or minus. Okay. So at what point would omega t become 0? Or cosine will go through a 0 when it's equal to theta. So would that mean that this is omega t plus theta or omega t minus theta? Okay, let's see if that is right. I thought I have a waveform somewhere. Okay, maybe I'll draw it. And if it is a minus, would you call it a lag or a lead? Lead, because the waveform is starting ahead of the 0. Yeah. And where it starts after, it's called a lag. And then often it's written as cosine omega t plus theta. So let's say your waveform is starting here. Let me use a different color. If the waveform is starting here, yeah, may not be correct. Let me So if it starts here, it should probably go through that point and somewhere there. So if you're talking about cosine, that would be the maximum. Something like that. So when you do omega t equals to 0, plus theta is when you get your initial point. Okay, so that's how your minus theta or plus theta would look like. And one of them is called a lead, and the other is called a lag. So we talked about frequency, amplitude, and you're also aware of what constant voltage sources, which are also called independent sources and dependent sources. So we won't look at those, but their behavior and the rules relating to those are similar. So going back to the mathematical form of the source, as I said, even a sine wave could be written as a cosine wave, and a cosine wave could be written as a sine wave, and so on. Often, a waveform is written this way, and it has a couple of features embedded into it, or information that is there. So one is obviously the starting point of the waveform, based on what we saw 2 slides ago. And the other is whether it's a sine or a cosine, which tells whether at certain time, whether it starts with the maximum or starts at 0. And then the maximum or peak value. And then the t indicates that the whole thing is a function of time. So as time varies, which is on the x-axis, the waveform can take different values. And there will also be a plus m and a minus m, which will be your plus Vmax and a minus Vmax. Yep. That's not a perfect waveform, but yep. And then there is also what is called the VRMS. So RMS is root mean square. You probably know about it. Are you familiar with this? So how is an RMS value calculated? So for example, the voltage in your house, the single phase voltage, is 230 volts. And that is a RMS value. And if you're looking at a sinusoidal waveform, the RMS value will be somewhere there, 230 volts on your 50 Hertz supply. Milliseconds. You should not show the frequency on this one. You should always show the time, but I'll put it there for information. So the 230 volts, as you can see, is not indicating the maximum value. It is indicating a certain value of your, or a portion of your maximum. What would the maximum be? Let's say if this is voltage, and I call this V peak or V max, and this is V RMS. So use the same formula. Vm equals root 2 times V RMS. So that will be root 2 times 230. Will be close to quickly calculating. 325. Okay. Now, do you guys know about this previously or not? Okay, that's good. There's also an interesting thing about this. I will talk. Probably let us see when we can talk about it. So let's talk about it on that slide by when I will finish some part of it and then give you guys a break. Okay, so the other things that we already touched are the time period frequency and angular frequency. The first two we touched already, frequency and time period. Angular frequency omega is given as 2 pi f or 2 pi over t and is often expressed in radians per second. Now, why do we need to be aware of this? Is, let's say we have Vm equals to sine omega t plus theta is V of t. So let's say we have a time-dependent sinusoidal source, and somebody gives you a value of theta and the maximum value that the waveform can take, and say, can you find the instantaneous value at a time t? Yeah. So it's something easy. Let's say you have a sine wave. Let's say theta is 0 to make it easy, so you can start from the origin, and you know the Vmax value. Yep. And if I say at time t equals to 3 milliseconds, what is the voltage value at 3 milliseconds? So that's the instantaneous value, isn't it? At 3 milliseconds. At 5 milliseconds, do you know what it is? The whole thing is 20, half of it is 10. At 5 is where the sine 90 occurs, which is the maximum value. So at 5 milliseconds, the instantaneous value will be same as the maximum value. At 3 milliseconds, how do we calculate the value? That's something you can work out during the break that I'll offer you in a minute. Okay, so remember that question. I will come back to it. The other thing is the phase angle. It fixes the reference position of the waveform at the time t equals to 0. So as I said, if you fix the x and y axis and move the waveform, you're fixing the position on the axis. And then relatively, you can say whether the waveform is starting ahead by a certain angle or starting behind by a certain angle, which we call lag. Okay. The other thing is changing this angle shifts the function along the time axis, but has no effect on the Vm or the angular frequency or time period. So as we have seen, moving these things can change only when it starts, but it doesn't change the actual values. So if I move this waveform ahead or behind, it doesn't change what the maximum value is. The maximum value is going to be the same. And the whole waveform is going to move, which means the time period which was here earlier and the new time period is over here. Okay? They're both the same. So the time period doesn't change, the maximum value doesn't change, the frequency doesn't change. So some of those things to remember. And if theta is positive, the function shifts to the left. So this is what we were talking earlier. Whereas if theta is negative, the function shifts to the right or occurs later. Is that what we did here? Yep. I'll tell you. This is definitely an issue of where people get confused. So as I said, where theta is negative, the function shifts to the right. Theta is usually given in degrees, blah, blah, blah. But if it is used with omega t inside the cosine term, it must be converted into radians. Okay. Again, we'll come back to this is another important point. So let's say this is sine omega t, plus 0 degrees, because there's no phase shift. And for omega t, as you plug values, you get sine 0 here when omega t is 0. And when omega t is 90 degrees, you get 90 and so on. If I then use a different color and say this is shifted by a theta. Now this is shifted to the right. If theta is negative, the function shifts to the right. So this angle is usually represented as omega t minus theta. So this one, sine omega t minus theta. So what does that mean? So if you start putting omega t equals to 0, omega t equals to 0 is this point. And that's not the same as sine 0, is it? It is something on the negative side. Okay? At omega t equals to 0, this sine waveform in green has a negative value. And when does that become 0? when omega t equals to theta, same as theta, yeah? So when omega t increases from 0 up to theta, then the whole thing becomes 0, and that's where your sine is starting. Okay? Does that answer your question? No. So this is what we call the lag, yeah? And the other one, where you move this way, you call leading. The values of angles you show here are one convention. And whenever you have a lag, yeah, although the angle is given as minus theta, you just take the theta and you do cosine of the theta to give you what we call the power factor. Yeah. And that power factor is referenced to be positive. Yeah. All lagging power factors are indicated as positive power factors. And that's where the confusion is. But to speak technically correctly, the power factor is either lag or lead. It's not positive or negative. It's just our imagination that a lagging power factor is positive and a leading power factor is negative. So if you drop that convention from your mind and say, okay, power factor can never be positive or negative. It's either lagging, leading, or unity power factor. And the only positive or negative associated is with the actual angle. Okay? Yeah. So people often do that and then relate it with the angle, which leads to an incorrect understanding. Okay. Yeah. Usually, lagging power factor is indicated as a positive value when doing calculations. A leading power factor, because you can say leading, but when you do the calculations, how does the computer or somebody understand from your calculation whether that's lagging or leading? That's where you use positive or negative. Yeah. But that positive or negative is opposite to this angle, which is where you shouldn't get confused. Okay, let me give you a break. I'll pause my recording. Okay, I've resumed the recording. So hopefully everybody can see my whiteboard. And the Zema function is Vm sine omega t plus theta. Yeah. U of t is Vm sine omega t plus theta. Now when theta takes so the initial condition, okay, let me draw. When theta equals to 0, you have your waveform like this. Agree? And sine omega t takes values of at 0 degrees for omega t. So when omega t is 0, yeah, we're here, sine omega t is 0. When omega t is so you can do 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180, 270, and 360. And we all know these values easily: 0.5, 0.707, 0.866, I think, and that's 1, 0, minus 1, 0. Yeah, that's for a typical sine wave. Now, if you then have sine omega t plus theta, yeah, which is which will go in here. And from our understanding, plus theta should make the waveform go to the left, yeah? So that's your theta. And at t equals to 0, what is the value of sine omega t plus theta? Let's say that's the maximum, then that should be 1. That means that theta is actually 90 degrees. Yeah? Shall we do a big one, or maybe let me erase this and do a little bit smaller theta. 90 is too big a jump. So let me just so that's 0, that's like 30, whatever, that's like 90, or maybe let's call this 45. Yep, and that's 180. So theta here is really 45 degrees. Okay? So when would at omega t equals to 0, what would be the sine value we know? So at omega t equals to 0, sine omega t plus theta will be sine 0 plus, because theta is 45 degrees, we do plus 45, yeah? And this should give you sine 45 degrees, yeah? And sine 45, or between 0 and 90, sine 45 is a positive value, so therefore it tallies with whatever that value is. Let's say that is 0.707. So at omega t equals to 0, this is 0.707. And we'll do a similar calculation with moving to the other side. Let me rub this on here, and I'll write it maybe here. So V of, yeah. So V of t equals Vm sine omega t plus or minus theta. That's what we're doing. If I now go to, that's too big. When I do sine omega t minus theta, yep. So what I'll do is I'll use the same sine omega t minus theta for this blue waveform that we have drawn here and see what value you get. So if omega is 0, yeah, then omega t minus theta should give me, here, should give me sine 0 minus 45 degrees. Yeah. Originally it is plus, but let's say if I'm wrong and minus is correct, then this is what it should look like. And that should give you sine of minus 45 degrees, which will be minus 0.707. Whereas our value here is positive and it's not negative, isn't it? Yeah. So therefore, omega t minus theta is incorrect for this waveform. And I'll prove it that it is correct for the other waveform we'll do. If we then do another waveform here. Yeah. And let's say that is 90, 45 will be somewhere there. So if it starts 30, 45, 60, 90, 120, 180, and that will be the point. Yeah, so it's starting after 45 degrees. So this is shifted right, and therefore my theory says it should be noted down as minus 45 degrees. Okay. And then if we do the same calculation as here, so if I do sine omega t minus 45 degrees, and at omega t equals to 0, what value it will have? 0 minus 45, or minus 0.707. If you extend this back, that is what you will have, minus 0.707. And when omega t is actually 45 degrees, yeah, when omega t equals to 45, so this value is minus 0.707. And at omega t equals to 45, that will be sine 45 degrees minus theta, which is also 45. So that should be 0. Yeah. So at this point, omega t is 45, and the theta value we got from the lag is 45 degrees as well. So, and we take it with a negative, so that makes it 0, which is correct because at 45 degrees you have your sine starting point. Okay, so basically what's happening is this whole set of values on the first column either shift up or down. Is that clear? Yeah. So that slide will be there in the recording, so you can go back and look at it. So the way the RMS value is calculated is, let's say you have a sine wave like this. How do I know that the RMS is 230 volts for a sinusoidal waveform and the peak is 325? So the way it's calculated is this whole sinusoidal waveform is divided into small chunks. Yeah, you may have learned this in maths, and at every time instant, yeah, you take the magnitude. Yeah, at every time instant there is a magnitude. And if I call this, let's say I1, I2, and so on, then RMS root mean square means first you take the squares, I1 square, I2 square, I3 square, I4 square, I5 square. Let's say divide it into five parts, and then you do the mean. So the mean of the squares is simply add the squares and divide by 5 because there are 5 of them. If there are 10, you divide by 10. And then you do the square root of that, which is the root. So root means square. That's what RMS means. So you sample the waveform or chop it into various segments, and each segment will be a sample. And for each sample at the time instant, you take the magnitude, square of it, find the mean. Yeah. So this number 5 is tied with this number 5. If you have 10 samples, then it should be divided by 10. That's how you do the mean, isn't it? If you have 20 samples, you divide by 20 to get the mean. And then finally, root, square root of all of that. That should give you the RMS value of that waveform. Do you guys know that previously? Okay, good. And remember, yeah? Okay, so moving on. So we talked about waveforms. The next is response of passive circuits. Passive circuits are where there are pure resistive elements, and L and C can be passive in one sense if they're in a DC circuit. In an AC circuit, they behave slightly different. You all know again how they behave in a single phase circuit, yeah? So in a DC circuit, ideally an inductor behaves as a short circuit or zero resistance path, and the capacitor behaves as a open circuit. Whereas in an AC circuit, the steady state behavior, I would call it the final behavior, is same as the DC behavior. But until that steady state is approached, the final point is approached, the behavior is changing with time, especially for the inductors and capacitors. And that changing behavior is sometimes useful and can sometimes cause a little bit of a headache. We'll learn more about it, or maybe you've already learned. Sorry? Somebody said something, I didn't get it. Okay. So you've already studied the behavior of L and C in your single-phase AC circuits, and also in your machines and power electronics module, you saw simple buck converter, and you saw how the inductor behaves, what it does, and how it's helpful for the circuit operation. So we'll not go further into the details, but what I wanted to show is all these basic relationships still hold good in a three-phase. And when I mean three-phase, we're only talking about balanced circuits, yeah, which means the current in the three phases is the same as drawn by the load, and the voltages are the same. And here's a simple circuit which probably you have seen previously in single-phase AC circuits that you learned. So if you have a sinusoidal source and a resistance, there's a current flowing through the resistance, and the current is a function of time, the voltage is a function of time. And if you plot those, yeah, so let me use a color. So this is my voltage, which is indicated by the red, and I will use a blue. This is the current, yeah? So you got a voltage and a current, and you can see the current starts when the voltage starts, the current drops to zero when the voltage drops to zero, and so on. And you can also see that the frequency or the time period is given here, whatever it is, omega t equals to 2 pi f. Yeah. Now, what is interesting is the power. So how do I get power in this circuit? Power through the resistor is simply V times I. So at every instant of time, I can take the value of voltage and the value of current, multiply them, I should get a value of power. And when voltage and current are positive, you get a positive power, which is shown. So here's the power waveform. Why did my color change? So this is the power. Now, as you can see, even though the voltages and currents are negative in this part of the circuit, yeah, because both voltage and current are negative, when you multiply two negative quantities, you get a positive quantity. So therefore, the power is positive. Agree? And one thing that you should note is the frequency of this power. So can somebody comment what the frequency of the power is? Twice as much as the voltage or current. Yeah. So power frequency is 2 times voltage frequency or 2 times current frequency. So power is called the double frequency component that happens. Now, the next interesting part is when we look at the same voltage, current, and power in an inductive circuit, this is how they look like. Yeah. Let me use some highlighters again. So let's say I use blue for the voltage. Probably I should use a consistent one. That's the voltage. And for the current, let me use a yellow. And because it's an inductive circuit, what happens to the current? Does the current lead or lag? Yeah. So or some people remember it as, yeah. So this is how I remember. In an inductor, the current is behind the voltage, so current lags. And in a capacitor, current is ahead, so current leads. So when you say current lags, that means the current starts after the voltage starts. So when the voltage is starting here, the current is starting here. If I represent the current with a yellow highlighter, so it's starting here, and the frequency will be more or less the same, except that it starts slightly later and finishes slightly later. And yeah, so usually in consumer distribution, voltage is taken as a reference because the expectation is that when you supply power to a residence or a building, you supply power such that the voltage available stays at 230 volts, no matter what happens. Therefore, that is our reference. And everything else, all the currents within the various loads drawn in that building are given as a reference to that voltage. Okay, so always, for most purposes, voltage is a reference, and the voltage at the load end is usually taken as the reference, not the voltage at the generator. Sometimes you may see when you did transformers, there's a primary and a secondary. You can draw the whole phasor diagram for the currents and voltages in a transformer, but you need to begin with one voltage as your reference, and usually it is the voltage on the side which is connected to the load. So if the secondary is connected to the loads, that secondary voltage will be your reference voltage, and then you start drawing everything. And this being an ideal circuit, yeah, so the phase lag between the voltage and current would be 90 degrees, which is what is shown here. And it's interesting to show it as 90. That's the reason it was shown at 90. So now, when I do the red highlighter for the power, so as you can see, between 0 and 90, what's happening with the voltage? The voltage is positive. Yeah, voltage is positive. Between the same 0 and 90, the current goes through a negative maximum and then comes back to minimum. So when you multiply voltage and current between 0 to 90 degrees, you should ideally get your power. Yeah, and that power would be positive or negative. Negative, because voltage is positive. Oops. Yes. So voltage is positive, current is negative, therefore power will be negative. And you can see that the power here, which I'm drawing in red now, is negative between 0 to 90 degrees. Yeah. And what happens between 90 and 180? The voltage is still positive, falling down. The current is positive now. Yeah. Up to this point. So therefore the power is positive until this point. And every time either the voltage or the current becomes a zero, the power becomes zero because it's a product of both. So at this point, voltage is zero, current is something. At this point, there is a certain voltage, almost maximum, but the current is zero, so therefore power has to be zero. Again, at this point, voltage is zero, but there's a certain positive current, but the power has to be zero, and so on. So that continues for the rest of the cycle. Now, in terms of the power waveform, which is in red here on this slide, and the power waveform here, which is in orange, what is the difference? Any differences that you can note? Yeah, so here the voltage and current are in phase, and also the power to some extent. But when we talk about power, you don't have to talk about phase shift anyway. Yeah, so here the power is all positive, and here the power is sometimes negative, sometimes positive. What does that mean? Yeah, but let's say you have a source, yeah, transformer outside your house, and you are the load. Let's say you are the inductor. The transformer outside your house is the source as shown in the circuit. When the power is positive, what does that mean? When the power is negative, what does it mean? Yeah, that's one good point, because if you do the average of that red waveform, what would it be? Yeah, average power is zero. So, as I said, if again the source is your transformer outside your house and the inductor is your node inside the house, what's happening is for first 90 degrees, 0 to 90, the power is negative, which means the power is being transferred from the load to the source. Yeah, and for the next 90-degree interval, where the power is positive, the power is transferred from the source to the load. And then it repeats itself. And because at regular intervals you have a set amount of power that's being exchanged between the transformer and your house, the net power, average power, is zero. Okay? I'll come back to it again. As on the power circuit, on this circuit, the power is always positive, which means the power is always being transferred from the source to the load, which is what you would expect for any load to behave, like you're drawing the power, so there should always be positive power flowing from the source to the load. Now, this behavior here is very peculiar because of the reactive element, which is the inductor and the capacitor. So what the inductor and the capacitor, when they're in the circuit, does is they allow for this power to flow between the source and themselves. And it doesn't do any useful work. It just occupies the capacity in the cable that runs between your house and your transformer. Yeah. Now I'll come back to why I said it's a capacity. So let's move forward. So here you have two elements, yeah, resistor and an inductor. Let's say the resistor is drawing the power as in the first case. Yeah. And for this power to come to your house, you need a certain size of a cable. Agree? And the inductance here behaves like this, where there is some power that is flowing between the source and the load. And that needs some space in the cable as well. So when you combine these two, the power that flows through your cable looks like the bold waveform here. Okay? Because in this circuit, there are two components, and we saw what each individual component behaves in a single-phase AC circuit. And therefore, whenever you talk about I square R as an indication of how much power is being dissipated and the current that needs to be accommodated in a cable, you should also keep in view of the reactive power that flows between the source and the load, which also needs some space in the cables. Yeah. So when you design cables for a DC circuit, if you say a 5 amp current is flowing through this piece of DC equipment, which could be a heater or something, then that's just 5 amps flowing from the source to the load. But the moment you replace the DC load with an AC load, and that AC load has let's say a rating of 5 amps on it, and it has some inductance in it, then that 5 amps might just be the pure resistive current, and the inductive current could be something else, which you need to take into account as well when you do sizing of cables. Okay, so I don't want to go further into this. Any questions? Yeah. Yeah. So in real life, most loads are like this, which they have a resistance and a reactance. There might be more resistance, less reactance, more reactance and less resistance, but it's always a combination of those two. And the reactance can either be due to an inductor or a capacitor. For example, if you have your compressor in your refrigerator, which keeps things cool, that acts as a source of inductance. So that's an inductive load. Your motors, they're all inductive loads. They have certain inductance values with them. And same with the capacitor again. So I won't go into the details of the waveforms of the capacitor. All it does is that current waveform should Yep. Mm-hmm. Yep. So an inductor by itself doesn't do useful work. But then an inductor, along with other elements, can be useful. Like I said, in the machines and power electronics module, you studied about a step-down converter. Yeah. So what is the inductor doing there? It's storing energy when the circuit is closed and when there's current through it, and when there is no supply, it gives out its energy to keep the load running. Yeah. So if you can make your circuit operate in such a way that the power flow into the inductor is when the circuit is on, and when it's time for the inductor to return the energy to the source, you cut off the source, so therefore it returns the energy to something else, which is also within the circuit. Yeah. Yeah. Just by itself, it doesn't do much useful work. Now, within a transformer is again an inductance. Although we always say that the reactive power, which is what we're seeing now, doesn't do any useful work, but bear in mind, in a transformer, the reactive power is what magnetizes the core, And the core magnetization is the key essential for the transformer to work. Agree? Yeah. If the transformer core is not magnetized, then the whole transformer action is not going to be there. And what magnetizes the core is actually the reactive current. And same with the motor as well. The motor action, the rotation produced in a motor is because of the inductance and the phase shift that it introduces, and therefore the angle between the two forces that result in a rotation. Okay, so here are some typical RL series circuit moving towards impedance rotation. So we started at single phase and moving towards impedance. So when you have an RL circuit, it's usual that you talk about impedance in an AC circuit, which is given as R plus JXL, and XL is calculated as 2 pi FL, where L is actual inductance value, XL is called the reactive inductance, and of course F is the frequency of the source. And only AC sources have a frequency. If it's a DC source, frequency is 0, which means XL becomes 0. Yeah. And therefore, that element offers 0 reactance, which is same as having a short circuit. And in a capacitor, it's 1 over 2 pi f. So when frequency is 0, 1 over 0 becomes infinite, which means the capacitor acts as an open circuit or a large resistance. And that's called the rectangular form, yeah, or Cartesian form of writing. Two components that are linked, and that's called the polar form. So we often use the polar form because it's easy. Sometimes it's also useful to work with rectangular form or Cartesian form. So an RL circuit is typically like this, R plus JXL. An RC circuit is R minus, note the minus, yeah, JXC. And if you have a combined RLC, then it could be something like this. It doesn't have to be XL minus XC. Sometimes it could be XL plus CXC as well. It depends on whether it's a series or a parallel circuit and so on. So starting looking again at that one, Z equals to Rx. Yeah. Of course, impedance is based on resistance and reactance, but then you can also calculate impedance from the voltage and current, similar to how you calculated resistance from voltage and current in a DC circuit. Yeah. And this one is in an AC circuit. So in an AC circuit, we don't talk just about resistance, we talk about impedance, which means it has resistance as well as reactance. And that reactance could either be an inductor or a capacitor. Yeah. And if you know some of those, you can calculate some of those. So here are certain calculations where if you know the value of R and X, for example, in a motor, because the motor is nothing but a wound coil, you know how much length of copper coil you wound, so you know the resistance, and then you can measure the inductance, and therefore you'll have the R and X value, and therefore you can give an impedance value. And if you know at what voltage you're going to use it, you know the voltage, therefore you can calculate the current. Again, all of these parameters here, voltage, current, and Z, they're all phasors. That's why they're written as bold letters. Whereas here, the phase is indicated separately. So you see the Z is not bold anymore, R is not bold, X is not bold. What I would suggest is when you write phasors, if you're writing by hand, always use a bar at the top. Yeah, it's quite difficult to get that when you type things. But when you write a normal equation, say Z equals to V by I, if they are phasors, just use that notation at the top. That indicates it's a phasor. If you don't, then it means it's not phasors, so there are no angles associated, in which case the whole thing might become wrong. If there are no angles indicated, then Z should not be Z, it should be R. Okay, that's about impedance. Impedance triangle, I think you're familiar with this. Yeah. So if you have R and X, you plot them in what is called an Argand diagram. And then you can find value of Z, or if you know the magnitude of Z and the angle. Yeah. So let's say if somebody gives you Z and the angle associated with it, you can always plot it here on a positive x-axis. That's the angle it makes in Z, and then you can complete the triangle, or you can use trigonometric relationship and find out the value of R and X. Any questions? Okay. Okay. So let's just do one more slide, then we can take a little break. So admittance is something that you probably don't come across easily. Have you come across admittance so far? Have you used anywhere in your calculations other than that one? You didn't, yeah. So usually admittance is similar to how conductance is opposite of resistance, yeah. So conductance G is 1 over R. Similarly, admittance Z is actually 1 over Y. Sorry, admittance Y is 1 over impedance. And the only place that I know where you use admittances is when you do the module called power systems. That's when you'll come across admittances. And sometimes, if you remember how you worked on series parallel combination of circuits in your very first year to find Thevenin equivalents and so on. So sometimes converting the resistance into conductances or impedances into admittances, which is the opposite of those parameters, it's easy to simplify certain things like that. And that's exactly where they're used in power systems in what is called as a load flow study. Yeah. When you perform a load flow study in power systems, that's where you use admittances. Now, what is load flow study? Load flow study is, to explain in simpler words, let's say on the UK power network, obviously there's more than one generating station, yeah? So let's say there are 10 generating stations located at various places, Manchester, Liverpool, blah, blah. The loads are everywhere. Let's say every city is a load. Let's say we have 15 cities. Now these 10 generating stations will supply the load to these 15 big cities, yeah? And at any given moment of time, you can find out how much each generating station is sending or pumping out its current and where the current is going. And obviously, those 10, let me just bring up a whiteboard, it might be easier to show it on that. So let's say you have a generator. Let's talk about just 5, yeah? And then you can have 6 nodes, and each generator is connected to, let's say, 1 node. Yeah. And then you can have loads connected to these points. Now, in this figure you're seeing, you have 5 or 6 generators and loads connected close to each generator. Now, if you visualize each of this as a small city where you have a generation and a load, and the generator supplies the load, all good. But then, what if there is a load that requires more power, let's say on this neighboring generator, and maybe you can say the load is 150 megawatt and the generator is only 100 megawatt. What do? We can either put another generator of 50 megawatts on that bus, or The step up will only change voltage, it won't increase the power, because V times I is the same on either side of the transformer. Yeah. So what you can do is, if there is excess power, let's say in this generator, yeah, but let's say if this load is 100 megawatt, but this generator is 180 megawatt. So there is an excess of 80 here. So this excess you can route here. Yeah. So these two can now operate together and meet their loads. And that is the advantage. So what happens in a power network is they try and make as many interconnections as possible so that power can transfer from one place to the other place depending on who needs more demand, who has less demand. And this is also exactly what happens between us and Europe, because we have one link that has been working for several years now between us and France. And there are two new links that have come on board recently. So whenever France has a bit severe winter than us, they draw more power and their generators cannot supply all of that. So at the same time, if the UK has a moderate, slightly high temperature, we use less heating loads, and therefore we have excess power available, and that goes to France. And sometimes it could be that the Atlantic is bad to us and our temperatures drop down, whereas France is slightly warmer, and some people jump over the channel to go for a holiday. But at the same time, most of us will be drawing more power to keep our homes hotter or warmer, in which case you're drawing power from the French grid. So all those things happen simultaneously. You can assume that that is the French grid, which is connected to the UK via several things. And when these interconnections are not there, it's often called as an islanding mode of operation, where everybody operates as an island. If there's a problem with the generator in that island, then all the loads there have no supply. Whereas if they have interconnections, let's say if this generator is gone out of supply, yeah, the remaining generators can still may be able to supply load through this connection. Yeah. So this connection is the power going to that load. And if there is spare in this generator, it will come through here. If there is spare in this generator, it will come through here and go to there. But because power has to transfer longer distances in this case, there might be higher losses, but at least the loads here are not losing the power supply. And that's the whole concept of having a power network or a grid. Again, I have to come back. Can't go too much into detail. Okay, so let's take a 10-minute break. Is that okay? Okay, let's see you 10 past or 12 past. Okay, so next thing to learn is time domain to phasor form. So on the previous slide, I've showed the different ways that you can represent a complex number. Yeah. And most of the impedances that we talk about, or currents and voltages, can also be represented in the same rectangular Cartesian form or also in the polar form. So for electrical engineering, the polar form is much more useful. The reason being, you can translate things between the time domain and the phasor form relatively easily by using what is called as a Euler's identity. We don't need to know what that is in detail, but there's a simple way to remember it. So let's say you have a current in a time domain form, which is given here. It is I max cosine omega t, same as like the voltage. We have V, function of time, is V max cosine omega t. And we also know that I max is same as root 2 times I RMS. Yep. And when there is no other angle here, That means the phase shift is sort of 0, or the current is actually starting on the origin of the y-axis. So if the first one is the time domain form, then the phasor form of that is simply I RMS at an angle 0. So what are the two things that we are taking from there? So from a time domain, you pick up the maximum value, divide by √2, you get the RMS value, and you look for any angle that goes into the angle. As simple as that. That will become the phasor form. So here's another example. If V is given as this one, then the phasor form is simply V RMS at an angle theta, because here there is an angle theta. Earlier it is 0, nothing is there, so the angle is 0. Okay? So that's the simplest way you can remember how to convert something from time domain to phasor domain. And you can do the same for vice versa. So if somebody gives you a quantity in phasor domain, let's say they tell you that the voltage is 230 volts at 25 degrees. Then you can write back into time domain form saying V of t is V max, which is 230 times √2, and cosine omega t plus 25 degrees. Okay? If the angle is a negative, that goes as a negative there. Okay?